Can you hear me okay?
Yeah.
Okay, awesome. So today we are going to talk about uh, these. So we will talk about the physical principles and that governs different physical properties. So this is basically the scaling relationship between different physical properties. We will cover 5 relationships here, and those are very fundamental. And in your exams, you will be given the problems. For example, like the distance is twice as big, and then how the different properties would change. Okay, so let's dive into the different relationships. So number one, this is called the gravity law. So that is the formula to calculate the gravitational force between two stars. So for example, like two stars are rotating with each other, around each other. So the Earth is rotating around the sun. So you can calculate what is the force, of star to the Earth, the sun to the Earth. So the formula is like this. So F equals to G. G is a constant, and M1 multiplied by M2 and divided by R squared. So this is the situation. So for example, you have one thing. This is the sun. That the mass is M1, and this is the Earth, the M2. So what is the force between the two? So this is the formula to calculate the force between the two objects. So for example, sun and the Earth, the sun and the Earth. Yeah. So the F equals to G. G is a constant, so that is universal all across the universe. So the G is a constant, and M1 is the mass of the first object, and M2 is the mass of the second object, and divided by R squared. So that tells you the force is proportional to M1, and this is proportional to M2. So for example, the Earth, if its mass is like 2 times larger, but the distance does not change, then the gravitational force is twice as big because it is proportional to the mass. And the gravitational force between myself and Ethan, if Ethan is 2 times bigger, and then our force, the gravitational extractions between us would be twice as large. So that is the proportional relationship between the M1 and M2. So the force would be proportional to M1 and M2. And the R square, and it is inversely proportional to R square, which means if the distance is increased by a factor of 2, for example, we are 1 foot away, and then we are separated to 2 feet away. So the force would be reduced by a factor of 4 because it had the R square over here. So if the distance is enlarged by a factor of like 10, then the force would be a factor of 100 smaller. So you can see that due to the R square relationship, the force would drop very significantly if the distance increase. Okay, so this is the first relationship that governs the dynamics of all the objects in the universe. So this is the most important force in the whole universe, because when the sun rotates around the Earth, it is well, the force will attract the Earth so that it does not fly away from the sun, but instead it will rotate around the sun. So this is the governing law behind all these orbits. Okay, so the second law is Kepler's second law. So what it tells you is, for example, this is the sun, and this is the Earth, and it moves at the speed of v, and v is short for velocity. And this is fundamentally the law that tells you that the angular momentum is conserved. It is constant, it does not change, because angular momentum equals to the mass of the Earth multiplied by the velocity and then multiplied by the distance. And the result is that in a specific time, the area that is covered by this trajectory is constant, because v multiplied by r and multiplied by a certain time, that is the areas over here. So this is constant. And what it tells us is that, well, if the distance is multiplied by a factor of, the distance is multiplied by a factor of 2, then the velocity would drop by a factor of 2 as well. But there is another formula here. So because it equals to mr square omega. The omega here is called angular velocity. So it tells you, for example, for a whole for the Earth to rotate, sorry, to travel around the sun. So that is 1 year, right? So the omega is you travel 360 degrees in 1 year, and that is 365 days. So the angular velocity is 1 degree per day, approximately 1 degree per day, right? So that is the angular velocity. So 1 degree per day. But so if there is another thing, that is, for example, mass, okay? Mass, we wanted to travel, let's assume that on Mars, it takes about half a year to finish, to travel around the sun, okay? And what is its distance? So from this, you can see that, well, the omega would be twice as big. Then to keep this constant, so the r square need to be a factor of 2 bigger, smaller, because omega is, let's see, omega is faster. Yeah. Omega is 2 times bigger, and r square is 2 times smaller. And if omega is 4 times bigger, and r square is 4 times smaller, and r is about 2 times smaller. Okay. Yeah, let's deep dive into this. Okay. Kepler second law. Joining a planet to the space interval as a planet orbit. Yeah. Planets do not move with constant speed along their orbit. Yeah. So a typical question would be like, for example, the orbit around the sun is elliptical, so it's not always the same. So the distance between the sun and the Earth is not always the same. So when you move to about let's assume that when you move to half of the distance of the current distance to the sun, and then your speed would be twice that big. Okay, so that is the thing here. Okay. The third formula is called Kepler's third law. So that is basically tells you the period, the relationship between period and the major axis length. As I said before, the orbit is elliptical, so it has a major axis. Okay. But we can assume that, well, we can ignore the details and assume it is a circle. The orbit is a circle. The orbit is a circle, and the radius of the orbit is a here. So that is basically the radius, okay? So what it tells you is that the time you need to travel around the whole orbit, and the time, for example, that is 1 year for the sun, okay? So that is 1 year here. So the square of 1 year is proportional to the distance between the sun and the Earth. Okay, but the Kepler third law is talking about a different object, the different, for example, Mars and the Earth. Okay, so when we are comparing two different objects that are rotating around the same object, for example, the sun, then you use the Kepler third law. But the Kepler second law is for just the one object. So, for example, the Earth. When it is closer and when it is further, that it will move at a different speed. So that is the Kepler second law. But the third law talks about a different object. For example, the Earth and the Mars. So let's assume that on the Earth, the T is 1 year, okay? And the A, let's assume it is a radius of 1, okay? So let's assume it's just the 1. And then we assume that now the Earth is twice, 4. Yeah, let's assume it is 4 times larger. So let's assume the radius between the Earth and the sun is 4 times larger. So let's move the Earth 4 times away from the sun at its current distance. So what would be, how long would it take for the Earth to travel around the sun? How many years do you need? So we can calculate that from
Like
here.
16.
8, I said 4, right?
I thought you said 2.
8. It should be 8.
Oh.
8 years. 8 times probably. Yeah. Let's do the math here. So first it is a to 3. So the cube of a. So that means a multiplied by a multiplied by a. And if a is 4 times bigger, so that is 4 times 4 times 4 equals to 64. Okay. 64. So pt squared means t multiplied by t. So t multiplied by t equals to, so this is 64. So t equals to 64 divided, the square root of 64. So that is 8. So you know that t now is 8 times bigger. That means if you move the sun, move the Earth 4 times away from the sun, then the time on it, so the time you need to travel around the sun would be 8 years. Okay, that would be 8 years. If you move, but if you move the Earth 4 times closer to the sun,
And the 8th.
then that is would be
Like
1/8 of the 1/8 of years. So that
which
would
is like
be
40 something days, I guess.
1.5 months. Yeah. Okay. So that is Kepler's third law. The formula 4 is Stephen's law. So what it tells you is that when how much energy would be emitted by a star at a specific temperature. So the formula is E equals to theta multiplied by T24. So this means the T here is the temperature. For example, the temperature of the sun is 5,500 Kelvin. Okay, and if the temperature increase by a factor of 2, so let's increase it to 11,000. Okay, so that's a factor of 2. How much brighter it would be? How much energy would it emit in a specific area? So this formula tells you that. So if T is bigger by a factor of 2, then the 4 means that the 4 T's multiply by each other. So that would be 2 multiplied by 2 multiplied by 2, 2 times 2 times 2 times 2 equals to 16. Yeah. So the energy for a specific area on this star emitted would be 16 times larger. So that's a lot. So if you increase the temperature by a factor of 2, a specific surface on the star will emit 16 times larger energy. So that is the relationship here. So in the exam, usually you would be asked to say, let's assume the radius does not change, right? And how much the luminosity would change. So the luminosity is the energy density. So that is the sigma theta multiplied by T24 and multiplied by the total area of the sphere. So that is the total surface area. So that is the formula is 4 times pi r squared. And let's assume that r does not change. So if the density, how the energy density would change. So if T is about 2 times larger, then what would be the luminosity? So the answer would be 16. And then it will, if you want to go further, let's assume that R would also change, right? The radius of the sun, for example. If the sun is it get hotter and get bigger. So let's assume that it get 2 times bigger and 2 times hotter, right? What would be the total energy that it emitted? How many times it would change? So that would be 16 here because T equals to T is 2 times larger, so that is 224, and the R here is also 2 times larger, so that is 222. So that is 4. So that is 226. Okay, so that is 64. Okay, so the total energy, if the temperature increased by a factor of 2 and the radius increased by a factor of 2,
I don't think
then
we'll
the
be close
total
like that.
would be 64.
Or just get like one of those things changing,
Okay, good.
probably.
Okay, the fifth formula is called a Wien's law. The Wien's law is something like to calculate the temperature, how the temperature determine the color of the star. So the color is basically measured using the peak wavelength here. Let's find a find another better one here. So precisely this is the Wien's law. Okay, so the lambda peak. So that is the peak of the black body emission, the peak of the distribution. Okay, so that means at here the star emit most of its energy, and lambda peak multiplied by T equals to 2.898 multiply times 10 to minus 3 millikelvin. Okay, a meter Kelvin. This is meter. Okay, the wavelength of the peak of the black body radiation curve gives the measurement of the temperature. Okay, so so if the temperature, for example, is 6,000 K, so that is about the temperature of the sun. So its peak, it will peak at around 483 nanometer. But when you if the temperature is a factor of 2 smaller, so that it drops to 300 Kelvin, and the peak of the energy would be I think it would double that, right? No, yeah, it would double that. So it would be somewhere here. Okay. Yeah, it will be somewhere here. So you need to multiply 483 by a factor of 2. So that would be somewhere around 1,000. So that it would be here. Yeah. So that is 986 nanometer. So it is in wavelength. So that means it is redder. Okay. So when your temperature is very high, then you have a bluer color. And when the temperature is very low, you have a redder color. So that is what the Wien's law tells you. And you can, and the tools are, if you multiply the two properties, the two numbers, and you get a constant. So that's amazing. So they are inversely proportional to each other. Okay. Okay, so this is the fifth law, the fifth formula. Okay. Then next, let's ask ChatGPT to give us some questions. and we can try to answer that and see how it goes. Okay, give me a question about Kepler's third law. Kepler's third law. See, it's an A here. Third law. Like if I move the Earth 4 times away from the sun, what would be the time needed to travel to orbit? Okay, 4 times further. Okay, so it tells you that if the Earth is moving an orbit 4 times further from the sun than its current distance, how long would it take to complete one orbit around the sun in Earth year? Okay, so you know that so the R would be 4. Yeah, so that is exactly the question I gave it. So I will answer. So because it is 4 here, and so that would be 8. It would be 8. Yeah. Let's see if it is correct. Okay, it tells you yes, exactly. The orbital period increased to 8 years when the distance is 4 times further. Okay, and it will give you a step-by-step calculation. Like the T new equal to 4 to 3, that is 64, and you take the square root of 64, that will equal to 80 years. Okay. Give me variance of these questions. Challenging me. Okay, this is a challenging variant of the Kepler's third law question to test your understanding. Okay. A planet currently orbits its star at a distance of 2 AU with an orbital period of 2.8 Earth years. If the planet is moved to a new orbit that is 8 times further from the sun, what will its new orbital period in Earth years? Okay, so 8 times further. Okay, let's do the math here. So this would be equal to 8. 8 times further. So let's make a calculation here. Can you do it, Ethan? If it is 8 times further, what would be the how many times it would be the period? Calculate it step by step. So the formula is here. So the R is 8 times bigger. Okay. So it is 8 multiplied by 8 multiplied by 8. Okay. Which is 512. And then you make a square root of this number. So 5.1. Frozen. Okay, so it would be 22.6.
22-ish.
Okay, so that will be about 23. And then you need to multiply it by the current term radius, okay? Current radius is 2.8 Earth year. So you need to multiply it by 2.8. So that will be 63.35. Okay. Let's see if it is correct. Okay, that's correct. Okay. That is exactly what we did. Yeah. So if the, got it? Okay. So I would encourage you to use ChatGPT to help you make some examples. And if you're stuck somewhere, then you can ask it to give you some hint and explain it to you. So I think now it should be very good given current situation. Yeah.
Aren't you allowed to bring calculator into the competition?
Sorry?
Are you allowed to bring a calculator?
Yeah, you can bring a calculator. Yeah. Okay. Okay. Let's do another demonstration here. So William's law. Let's do Stephen's law. So what is Stephen's?
这个考试，我考一下。
Okay, so you know that this is Stephen's law, and give me a question about Stephen's law, like if the temperature of the Earth, actually the Sun, is 2 times higher, what would be the total luminosity of the Sun if the radius does not change? Okay. So you can see this is a formula that I showed earlier. Yeah, so I can say, yeah, it should be, well, what is the answer? If it is 2 times hotter, what would be the luminosity change? How would be the luminosity change? 你又小台，你又小台。T24, what does T24 mean? How did you get it? How do you get the 16?
Like 2 times 2 times 2 times 2.
Yeah, correct. Yeah. Okay. It tells you, yeah, it is correct. Because temperature is 2 times bigger, and the 224 equals 216. Okay. Give me a similar problem, which is more challenging. Okay. So if the radius triples, okay, so it changed, okay, and the temperature increased by 50%, so that's 1.5 T. Okay, how do you calculate it? How do you calculate? Tell me how to calculate it. Temperature is 1.5 bigger, times bigger, 1.5. How do you calculate it? Just tell me the equation. It is 1.5. That is for 1.5, right? 1.5 times 1.5 times 1.5 times 1.5. And then the radius.
Times 3.
The radius is a factor of the power to 2. Okay. So that is 3 multiplied by 3. Okay. That would be 65.56 5625. Okay. So let's try it. Action draw. Right. Let's see. Yeah. Yeah, that's it. Yeah. So I would encourage you to use ChatGPT to give you some problems, and you can practice, and it can check with you. Okay. Okay. Any questions? No. If no, let's call it a day. Okay. Thank you all.